We'll talk about why do I like ROS a lot. And that's because of some specific library support. And because there is some specific library support, it becomes absolutely great. Very briefly talking about the action library. So one of the most naive things that we did was you go to G1, G2, G3, G4, and using your own simulators, it was actually pretty easy. Now in this I said that let's assume that there's a motion planning go to goal that is always available. And this is also possible because I have my motion planning plus localization plus control, which are running in parallel. So let's talk about this thing about a little bit more. This is called as a navigation stack. And what it does is that I've got my deliberative motion planning, that supplies a sub goal. Now with ROS there are two notations. Sometimes I just write the name of the topic like this, and sometimes I put it explicitly as a square bracket, as a box. So we've discussed a lot of ROS, so let me just write it directly rather than putting it as a box. So it provides a sub goal to my reactive motion planning. In fact, the deliberative motion planning, it provides a trajectory. The trajectory goes to a fusion algorithm that provides a sub goal, and is already existing, so you don't need to worry about it, to my reactive motion planning algorithm, which provides the move to the control, which controls the physical motor, and that's not in the part of ROS because that's hardware. So as a hardware, it controls the physical motor. The fusion will also need the pose, or I have the localization. The motion planning will also need the global map, which is produced by a SLAM technique. So there's a map server which actually provides with a map. Right over here, and the map is also used by a fusion. The localization is done using LiDAR sensor. Let's only take in one sensors. And the reactive motion planning also takes in the LiDAR sensor. Now this one is actually interesting because last time if I had to show A, B, and T1, this is how I'm drawing. Previously I drew exactly the same thing as T1 and a B and a C. Both of them are equivalent. So when I put a box, I say that A is writing to T1 and there are multiple subscribers to T1. So I just put it on the topic. But then when I just write down without the box, then I have to draw multiple edges like this. Both of them are exactly the same. Okay, so the deliberative motion planning also listens to a topic called as goal. and there's some program that will supply it. Now this is the user control program. That's my sequencing program. And we also have a, let's say, a local map. And what does it do? It the reactive planning, motion planning, of course, it uses a lidar, but then sometimes it's only working based on a deliberative planning, which is working on global map. The global map does not have moving people, because when SLAM happened, when this map was made, the students were asked to move out. So no students moving around, no research scholars moving around, no faculty moving around got registered. So let's say there is a local map as well, and the local map is made with the help of LiDAR, of course, and the position. Now this thing is already up and running. So if you want to move a robot, you just need to write down the goal and you'll get to move the robot. So if I have to move a robot to G1, it means I just publish G1 to goal topic. And that's all. That's all that I need to do. I just need to publish G1 to the goal topic and my robot will autonomously go to the goal. And once my robot will automatically go to the goal, I am done. Now, we are talking about library, so I did make a mention of the motion planning library. At the deliberative level, the open motion planning library is the most common. For localization, the adaptive Monte Carlo localization, which is just a particle filter, is with adaptive number of particles, that's more common. SLAM, of course, G mapping is most common. And this entire thing is called as the move base suit. So this entire thing is called as a move base suit. And there's another library which handles all the transformations. So every sensor is a transform in itself, every actuator has a transformation itself, every object has a transform itself, and robotics you're looking about multiple transformation. So the LiDAR is a coordinate access system, the robot is a coordinate access system, the world is a coordinate access system, the motors are another coordinate access system. Some of them, and so the TF is, this is called as a transformation tree. And each one of these edges, so each one of the vertices shows coordinate system, access system. And the edges show the transforms between the coordinate access systems. And I can, if I need to know the transformation between robot and motor, it's stored here. If I need to show the transformation between LiDAR and motor, I'll transform this to this and this to this. So I'll get it. And that's why it's a tree, because if I make it in the form of a graph, world to motor will be a transformation T1, but there'll be another transformation from world to robot, robot to motor, and if both of them are not equal, there will be an ambiguity, and therefore we restrict to a tree. This is robot to LiDAR, so which is where is the LiDAR in the robot coordinate axis frame. This is called as a static transform that does not change with time and can be pre-specified in the configuration file. Robot with respect to world, which is the pose of the robot. This is dynamic and should be continuously published by a script. In our case, the localization system. So that's why I don't do transformations as well. I just take it as a transformation library. So go to exactly the same program, which is that I have to go to G1, then G2, then G3, then G4. Normally, this is what program you imagine. Go to G1, then go to G2, then go to G3, then go to G4, which in ROS will mean publish G1 to goal, publish G2 to goal, publish G3 to goal, publish G4 to goal. Now there's a problem over here because if you run this program, this publishes nothing but a networking channel and you're sending a message to the networking channel. So sending something to a networking channel is very fast. So you'll give G1, G2, G3, G4, and goal has a queue size of say 1, so it only takes a recent goal. So even before the robot reaches G1, it will be overwritten by G2, will be overwritten by G3, it will be overwritten by G4. The motion planning library continuously checks for is there a change of goal, and it always takes the latest goal and makes the robot move to that, irrespective of whether the robot reached the previous goal or not. So the robot will actually directly reach G4. You're publishing it onto the networking channel. Now, if you really want to go on this one, then it's actually interesting because then I need a feedback, and if you need a feedback, then luckily a feedback is provided by the move base. So a feedback is provided by a feed base, and you could register for a feedback channel. The feedback will be true, goal reached with success, or false. So now let me change this program. So of course I need to change the program. So first let me make in the callback for feedback channel. So I need to register a function that's called as the callback for feedback channel, and it'll get the feedback as input. Here is where I say if current goal was G1 and feedback was okay, then publish G2. Similarly, G2 to G3, G3 to G4, and G4 to stop. Stop is basically you tell nothing to do. And now my actual program, so that's my feedback function, and now my actual program is register feedback channel. Okay, let's give it a name. Register callback for feedback channel. So I'll have to tell the event manager that I'm interested in whatever communication happens over here because I want to read all OKs. Every time an OK comes, I change the goal. So I say register callback for feedback channel. So register this function with the event manager over topic feedback. And do nothing. First one always needs to be published. So I say publish G1 to and then do nothing. Now you can see that, I mean, this is how easy the program was in any of your created simulator, and it's become a difficult logic. So the logic is difficult. So it says that there's a networking channel which is feedback. Every time something comes in this feedback channel, every time a OK comes on this feedback channel, I then give it the next goal to publish. So that's my program. This is, say, the move base. So every time a OK comes, then I give it the next goal. Every time a OK comes, then I give it the next goal. Every time a OK comes, then I give it the next goal. If you like it, then that's one option. Of course, there's another option that you can make a server. You can make a service. So let's make motion planning as a service. Now I do, so motion planning service dot send request G1. A response will come, which I hope will be OK. So let's say if it's not equal to OK, then terminate. I'm not sure what can we do. The robot cannot reach the goal. Then I say response is equal to motion planning service dot send request G2, and similarly G3 and G4. That's a neater program. So I send a request, and request response happens by, if you send a request to a service till you get a response, there's nothing that your control of the program goes away. So the control of the program goes away, and I'll not get the control of the program back again till I get a response. It is neater, but sometimes what happens is that the BFSM lectures that I took, the robot is going to G1, but master calls. Then the goal suddenly has to change to master. When master calls, you leave everything and go to the master. When there's fire, you leave everything and go to the exit. So here I cannot change the goal. So in this mechanism, I cannot change the goal. So request is done. I'll only get the feedback back either when it fails, or I mean, like, it will fail when there's no path to the goal, or somebody is blocking characteristically, or I have reached the goal. I cannot change the goal here because till I get a response, nothing is happening. And that's the problem, that sometimes you send a request to a server, it's calculating. You want to change a few numbers in the formula that you gave, but then you can either terminate the entire service, or you just wait for the response to come. There's no way that you can update your goal. There's no way that you can update what you are doing. And there's a problem around over here. So the action library is one interesting way to handle all this. So action library is for actions. So actions are the ones which take a long time. I'm not going into the details of the action library, but then basically what you do is that you have exactly the same way on a request response basis. So you send a request service, but then the control of the program comes, and then you could either wait till a response comes if you anyways have to go. So I send G1. I can either wait or based on any other condition, I can say update goal. So it'll look at the physical service, it'll look at the entire navigation stack, and it'll send the updated goal. And the robot will now start going on to updated goal, where this condition is, of course, it could be based on an external input, it could be based on another callback function, it could be based on absolutely anything that you put up. So quickly summarizing whatever we have seen so far, we talked about creating simulations. So just empty arena where I could drag and drop different robots and entities, and everything was okay till there was only graphics. How does it look onto the screen? So you have similar things to 3D rendering libraries. You can change the visual camera and see, and each of the things could have a support of a physics server so that the impossible doesn't happen. There were endless number of libraries, so anything which is possible as library was available as library. Collision detection, proximity checking, motion planning, control, to inverse kinematics, to forward kinematics, to grasping server, to transformation server, to 3D vision, to 2D vision. Everything was absolutely available as a library for me, and all that I had to do was to write down programs. But then in the programs we saw that the problem was there are too many scripts which are running in parallel, and in parallel because they work on different frequencies, and because most of the computer architectures are now parallel, multiple cores, GPUs, so everything has to be in parallel. And unlike any of the matrix multiplication or any of the typical GPU operations, here the parallelism meant that there is a lot of information exchange that's ad hoc in basis, and these could even be physical multiple different servers. So we created a system where the data could be shared across all nodes. So if some data concerns 5 scripts, the same data could be given to all 5. And we handled an event-driven mechanism where I, who needs data, just registers to the event manager a callback function, and I don't continuously ping and ask for more data. And using that, we looked at specifically how ROS handles it, and took in a specific example superficially of navigation stack about how information exchange is going, and how I can say go to goal is a basic behavior because everything is running in the background. And then we looked at the action library, which is basically saying that I need 2 functionalities to be there simultaneously. One, that my goal based on some condition should continuously change. And second is that how many OKs have come, and based on that I have updated my current goal is not something that I was calling as a good architecture. So the action library was something that was supposed to handle long-term actions where I give it like a request response system and it's running, and whenever I need to change it based on condition, I get the control back and I can actually ping it, or I can choose to just wait for it. And using this, we are in a position to really look into the actual robot operating system as a set of programming exercises, which is what we'll do next.